Ramesh is still trying to stream it on YouTube as well as record it. And after that, I will also ask Professor Jitendra Singh Sangwai to introduce you.
Okay.
Yeah.
You're good to go.
Okay. So thanks again, Professor Deo, for accepting our invitation and to give a talk in the Subsurface Mechanics webinar series.
To stream it on YouTube as well as
at IIT Madras. So I would like to request Professor Jitendra Sangwai to introduce Professor Milind Deo as a speaker for tonight.
Okay, thank you, Chandra, and thank you, Professor Deo, for accepting our invitation to be a part of this webinar series. And we are really grateful to you. So let me introduce Professor Deo. Professor Milind Deo is the Peter D. Catherine R. Professor in the Department of Chemical Engineering at the University of Utah in Salt Lake City, and interim director of the Energy and Geoscience Institute. He has a BS from IIT Madras in India and PhD from University of Houston, all in chemical engineering. He was a postdoctoral fellow at Stanford University before joining the University of Utah faculty in 1989. His research interests are in nanotechnology as it relates to energy, reservoir engineering, enhanced oil recovery, carbon dioxide injection for UR and sequestration, flow assurance, and geothermal energy production. He was the Associate Dean for Academic Affairs in the College of Engineering and Department Chair. He has supervised the PhD dissertation of about 35 students and the master thesis of about 15 students. He is a fellow of the American Institute of Chemical Engineers and was one of the distinguished lecturers for the Society of Petroleum Engineers. So we are really very happy to host Professor Deo as a part of our webinar series. And I request Professor Deo to please have his talk on the pressure-driven fluid flow under confinement. Professor Deo, please.
Thank you. Thank you, Jitendra. Thank you, Chandra, for the invitation. It's my pleasure to join you today, particularly because I am, in one sense, one of you. Being from there, even though it's 40 years ago, I remember my IIT days very fondly. I think those 5 years, actually, those were 5-year BTECs at that time, were very formative in how they helped us essentially become, I guess, men from children, I guess, in some sense. So we grew up in that environment. So yeah, thank you. I was there. I hadn't been there for about 20 years or so, and then suddenly, because of circumstances, I ended up coming to IIT 2 or 3 times within the 2 years, and I did give a talk about 3 years ago. And I see that there is a lot of change and progress, and I'm particularly happy to note that one of my classmates and dear friend, Professor Nagarajan, is the head of the department there and leading the growth of the Department of Chemical Engineering at IIT Madras. Anyway, so today my talk is on pressure-driven fluid flow under confinement. I will start by giving a very quick introduction to our center, the Energy Frontiers Research Center. This research center is funded by the Basic Energy Sciences. The director is Daryl Butt, and I'm one of the associate directors. We got started in 2018. The mission of this center is to synthesize materials with hierarchical porosity and study fluid and other types of behavior in these type of systems. The hypothesis or the premise is that the behavior of some of the materials, fluids, even reactions under conditions where the materials and fluids are in very small pores is different from what we expect them to be based on our understanding of the physical laws. And that's why the idea then is to make materials that have established calibrated structure and then study properties in them. So it's a pretty straightforward work plan in some sense. But of course, it's easier said than done. And we came at it from a geomaterials perspective, you know, there are a lot of people working in nano confinement, and there are people working in sensors, there are people working in membranes. So we come at it from a geomaterials perspective. And why is that? In some sense, again, it was driven by this very large growth in shale oil production in the US. As you can see here, more than 70% of the crude oil production of 12 million barrels a day comes from these shales, so-called shales, in various parts of the United States. And there are some anomalous behaviors that have been noted for these shales. Some of you, of course, are very familiar with this field, but most of you may not be. You know, the productivity of a reservoir is based on how the proportion of gas and oil or liquids vary over time. So in some places in these shales like Bakken, for example, you see there is a significant delay in the arrival of significant amount of gas. So what we call free gas production, it takes several years for this to happen. So one hypothesis was that the behavior of these multi-component gas mixtures in these complex reservoirs, which are characterized by nanopores, is different from the conventional reservoirs where the pores are of several micron size. And again, understanding that was one of the motivations. And of course, another motivation was reduction and more responsible use for water. That means understanding how water flows in these systems, first of all, by itself as a single phase, and then later in a multi-phase context. And then, of course, there is a big interest in understanding the behavior of carbon dioxide in the system, because these are established, very large repositories that can then be used for storing carbon dioxide. Anyway, so this is basically the societal motivation. As you know, the energy and environment is the defining question, I guess, of our generation, where we need to provide adequate energy with minimal or no impact on the environment. It's a significant challenge. Anyway, so that was one of those were the societal aspects. And then it has applications in all of the other things that we talked about, sensors and separations of various kinds. So the 4-year goals of the center are to develop basically this fundamental understanding of confinement, because BES, the Basic Energy Sciences motives or the mission is fundamental science, is to really understand the physical phenomena that govern some of the important things that affect the various technologies that we're interested in. So I'm going to focus more on that first part, understanding the confinement. We are also looking at the effect, as I said, since we came at it from the geomaterials perspective, understanding the mineralogy and material heterogeneity and its impact on flow and thermodynamics, looking at these fairly high-end inoperando methods, the small angle neutron scattering, small angle X-ray scattering, ultra small angle techniques, to look at phenomena as they actually happen under high pressure. And so there is a big group of people that is looking at that. I'm not going to talk about it today. And then tie everything up using multi-scale models and multi-physics descriptions. And I'm going to talk about this quite a bit today on how we did that for some of the experimental observations that we have. And these are our partners currently. We are the prime, and then Cornell, University of Buffalo. Actually, we got this recently assigned as one of our partners. University of Wyoming University of California, Davis, and our national lab partner is Idaho National Lab. So the idea is to design these materials that have pore structure well defined. So the idea again is to create this hierarchical porosity, which is evident in geomaterials at the different scales. So initial strategy was to make particles using sol gel techniques such as SBA15 or 16, and then use spark plasma sintering to put that together into a robust structure so that we can then study the properties of fluids inside these materials. One of the difficulties with that is during sintering, of course, you get compaction, but also sometimes cracking and other defects that now we have figured out how to address. But as you can see in these materials, this is actually a TEM from the FIB of one of these discs that we made. You can see the preservation of the nanostructure that we intended to create at that scale. And then we have made good bit of progress in creating materials that have only the nano materials. And then we have, as I said, I'm not going to talk in detail about this, but we have this defect healing strategies that can create materials of interest. We also have a nanoscribe at University of Utah, and one of my graduate students is working on templating. First, make a template using the best resolution we can get out of the nanoscribe, which it happens to be around 100 to 200 nanometers, and then fill it up with materials that go to the single-digit nanopore structure. And we are, again, reasonably successful in being able to do that. And finally, to get actually into the geomaterials aspect of it, we have also been able to image and extract pore structures from shales themselves and then print it using nanoscribe, not at the single-digit nanometer resolution, but tens of nanometer resolution. This paper was published in 2020, actually. So what do we do then with these materials? We can study how densities vary. There is a specific technique that we use in doing that. We can look at phase transitions using differential scanning calorimetry, which we have done quite a bit, and we have a few papers in this space. And then again, try to explain the phenomena using either molecular dynamic simulations or higher scale simulations. And I'll talk about that in the flow context. So here you can see that you see multiple peaks in DSC, indicating that you have a peak that is associated with the bulk and a peak that is associated with confinement, showing two different the effect of what's going on under confinement. From the pressure-driven flow perspective, once we have a robust material or a disk that has been well understood, the pore structure of which is well understood, then we can put it into our high pressure flow system and perform flow versus delta P measurements. This is actually a model that shows some of the things that we have been doing from a molecular dynamics point of view. And we also have a miniature core holder that we can put into. This is not a nano XCT, but a micro XCT, X-ray tomography, to look at porosity changes, or how fluids fill within the different porosity structures that are present in the materials that have been made. And since these type of, at this scale, we cannot use molecular dynamics, we are using dissipative particle dynamics, or DPD, to simulate flow and understand what is going on. As I mentioned, I think earlier in the introduction, we do have a very strong link to the mechanical aspects of how properties are being affected by different mineralogies and heterogeneities in the system. And we're using a pico indentation method and then modeling using the various tools that are available to us. And here is where Pania Newell from mechanical engineering is involved in this work. And finally, we are working with Adri Van Duin at Penn State to look at the different reactivities as the materials form and the materials react under different conditions. We are more interested in clay transformations. That's the illite transformation that are shown here, or carbon dioxide reactions with different minerals. Anyway, so that's more an introduction, I think, to the center. Now I'll focus more on the main results of the pressure in confinement. And if you have some time, then I will go into the thermodynamics component of the talk. So what is the nano confinement? For those of you who are not very familiar with it, in pores that are large in diameter, you expect Haagen-Poiseuille relationship to hold. So basically, the pipe flow relationship that we both as chemical engineers and fluid mechanicists are very familiar with. But as we go into smaller and smaller pores, and as the fluid molecule, the size of the fluid molecule gets to be of a similar scale as the pore size itself, then the surface effects of due to the wall and the clustering or the orientation of the molecule within the pore can start affecting the flow behavior. And people have noted for quite some time, I think now, particularly in carbon nanotubes, a very large, what they call enhancement. So more flow compared to what you would see in continuum relationships. So here is a table, summary table. These are by no means all of the references in this area. There are literally hundreds of papers in this space. One of the main ones that has been cited quite a bit is this Nature paper from Maynak Muzumdar et al. In 2005, which shows enhancement factors of several orders of magnitude in carbon nanotubes. Then there have been other studies, both experimental as well as, so they used these very thin membranes to establish this effect. The later CNT studies did not find this level of enhancement, but some similar orders of magnitude. But then on the other hand, there have been some recent studies that have shown, even starting actually from 1950s in Y-core, these are experimental observations that have shown what is called negative slip, meaning there is actually flow reduction rather than flow enhancement. So since we are dealing a lot with siliceous materials in subsurface systems, we wanted to figure out where are we in this space? Are we on the negative side of things? So basically, if you were to take one thing away from my talk today, it would be to answer this question: are we in this realm or on this realm? I'm trying to answer that using various pieces of evidence that I'm going to show you today. Okay, so one of the things that we did was to try to repeat what has been done in CNTs for some time, But here we looked not at water, of course, was one of the things that we did look at, and you can see the enhancement factors for water. This is the Haagen-Poiseuille line, are several orders of magnitude higher as the diameter of the tube increases, the enhancement goes down and starts moving towards continuum. But we also looked at, since we were interested in hydrocarbons, long chain hydrocarbons as they evolved. These are molecular dynamic simulation. These are not experimental work. But we did not see the type of enhancements as was seen for water. This is somewhat expected because obviously this is a hydrophobic system and we are flowing hydrocarbons. But even then we were able to see moderate enhancements of the order of 2 orders of magnitude in CNTs. And so anyway, this is the same views. There are some interesting features that we see. The decane molecule, for example, starts flowing more or less like a corkscrew. And that's one reason why you see even a large molecule like decane flow with the same efficacy as something like hexane, because of the way it reorientates itself and flows through the carbon nanotube. And this just gave us some indication of how these hydrocarbon systems behave. But again, the takeaway from here is that at least we did not see, with the type of method that we used in our MD simulations, the type of enhancements that some of the other people had observed for hydrocarbons in CNT. So this is for CNTs. So one of the experimental technique that we used in looking at flow in silica channels is packing capillaries using these perfectly sized colloidal particles. Again, these are not simple experiments by any means, but once the capillary is packed, you can see a picture of the particles here and how the fluids actually fill within this particular system. And then we looked at flow versus delta P relationship in that system. And these are experimental results for hydrophilic silica. So these colloidal particles packed, it's a hydrophilic system. And as you can see here, for water, again, we see very moderate or almost no enhancement at all. And for hexane and a similar sized polar molecule, methanol, we see enhancements of the order of, these are much larger pore sizes than we would have liked in this particular case, but with the molecular size of particle size of 177 nanometers, we are looking at of the order of about 15 to 20 nanometer pore size. So it's about a tenth as you go from the particle size to the packed pore size. So here we are not looking at the Haagen-Poiseuille relationship, but we are looking at the Cassini-Kármán relationship. And there was a paper, I think back in 2012 or something, by Rogers and Wirth, that looked at the same system, so in a mirror image. So they actually salinized it, so they made it hydrophobic, and they observed enhancements for water in that system of the order of 50 or so for the smallest particles that they used, and almost a zero enhancement for, so essentially for toluene, so no effect for toluene, but which again, they explained by saying that you're looking at a hydrophobic system, so the surface fluid interactions would dictate that the water would have enhancement. But again, the enhancements were of the order of 50. But you should observe here that the Cozzini-Carbon relationship, by the way, has some empiricism built in it because of the tortuosity aspects of it. And it has a porosity term in it that you have to really characterize well, because it has, as you can see, a significant functionality built into that relationship. So if there is a small change in porosity, it can affect the results significantly. And if you think that your tortuosity, I think it's a factor of about 2.5, if not what you think it is in your particular system, then the results might vary. So to me personally, I feel that changes of the order of 5 or 10 could be because of some of these other effects that we might be looking at. So I would say that the system more or less behaves like continuum if you see effects of this kind. So going further, we then looked at the molecular dynamic simulations of the different fluids that we actually did experimentally. So this is water. We did not, so these are silica tubes now. And I think these type of simulations have not been reported in our paper is in review. It has not yet been published. And instead of seeing very much enhancement at all, we start seeing some reduction. In fact, at around 1 or 2 nanometers, there is the water does not get into the system. For the 3 fluids then that we looked at experimentally, water, hexane, and methanol, we start seeing these are actually densities, how densities vary in the different pore sizes, going from 1 nanometers to 8 nanometers. And here is that enhancement that we are talking about. For all of these fluids, we see flow reduction like had been observed in that 2016 experimental paper for Vicore. Okay, so that's one of the things that we see. And we see this happening because of what we call a sticking layer or a zone of no flow at the pore wall because of the affinity of the fluid to the silica surface. And the biggest sticking zone that we have is for methanol, and it also has the highest reduction. So instead of slip, we have a stick or negative slip, as been pointed out in the literature. So I'll provide you with some additional evidence. We did some experiments as well as models, again, molecular dynamic models with different surfaces. So talc, which is an OTS, which is silane, which is, so we looked at sessile drop contact angles, both with MD simulations and experimental, and we were able to match them reasonably well. So these are hydrophobic and these are hydrophilic surfaces, the amorphous silica and quartz. And the molecular dynamic simulations of flow in these channels, now these are not tubes, but cuvette flow in these shows, again, very small enhancements in the hydrophobic systems and more or less no enhancement or reduction in this is for water, in the hydrophilic system. And this paper has been published in Colloids and Interfaces. Again, more evidence to see how the organization of these fluids at the surface affects. So we see an exclusion zone here for the hydrophobic surface, and more or less for the dipole angle, we see essentially a fairly ordered structure for the hydrophobic systems and a free OH layer for the hydrophobic systems and a more ordered systems for the hydrophilic systems. And that's again confirmed using some frequency vibrational spectroscopy. So again, quite a bit of evidence from different surface materials and different experimental systems. Some of these experiments at the nanoscale are very difficult, particularly the pressure-driven flow, because you actually have to seal the materials at very for high pressure flow. So eventually we will have to do the experimental validation or confirmation at larger scales, right? Even that capillary that I showed you was a 75 micron capillary. So to model the flow in that a complete system, we need to go beyond molecular dynamics. And one of the techniques that we have been using is this dissipative particle dynamics, where we not only look at the overall fluid behavior, but also properties like viscosities and things like that. Here, most of this work is done by our partners at Idaho National Lab using their supercomputers. The idea is to to scale it up from the nanoscale that I had been showing you all this while to the micro scale, where we either look at the entire phenomenon or parts of it. The technique itself and some of the results that we have obtained have been published by a couple of our papers in these journals. I'll not dwell into this, but basically it's a very powerful technique that has applications from liquid vapor transition, which I'm not going to talk about today, but looking at multi-phase effects, which we are investigating fairly in detail in our center, but also in other phenomena. And then scalability has been quite good in the newest Summit supercomputer that Idaho National Lab currently has. So first, we had to validate the techniques using the molecular dynamics that I had shown you. And here the focus was more on viscosity behavior, because there is another factor to the change in physical laws under confinement, and that is viscosity. So we don't know if the viscosity values that we are using, by the way, all of the viscosity values that I showed you during the comparisons between continuum and confined flow were bulk values. So bulk viscosity values were adjusted for pressure, but they were still bulk viscosity values. And we are also very deeply interested in trying to figure out what happens to viscosity under confinement. And here are some of the effects that we see using molecular dynamics, that we have this decrease with pressure gradient, center to wall effects, decrease with strain rate. Again, permeabilities are less than what we see in the Haagen-Poiseuille relationship. And there is some molecular orientation effects that are similar to what we have seen in the simulation that I showed you. So DPD, when we go to the higher scales, we end up seeing more or less the same type of relationship as you see here with respect to the local viscosity behavior. The local viscosity decreases with increasing pressure gradient and decreases from central to near wall. So the higher scale models which we need for validating or for comparison with experiments which we can only do at certain scales captures the behavior reasonably okay, but it should be noted that it's not all perfectly scaled. We do have some changes because of the orders of shear rate in the MD and the DPD. On the permeability side, we do see that the permeability, that a pressure threshold needs to be satisfied before the fluid will actually enter the system, and the permeability increases first and then reaches a plateau. And the more important thing is that in most of the simulation that we saw flow reduction instead of enhancement. And the slip length in most of these cases tends to be negative, not positive like we had seen for carbon nanotubes. So the main summary, or again the takeaway from what we have seen so far for flow in confinement, which is what we have been trying to answer, that what question, do we see these significant enhancements? And if so, what is the order of these enhancements? Our investigations at least show that they are not significant in the systems that we have seen compared to CNTs. And then depending on the type of fluid and the wettability of the system, we actually see more of a flow reduction. And this will have more of an impact in multiphase flow when we start looking at the multiphase flow components of it. I have to, there's a caveat here that we do need to consider the density and viscosity changes, as was shown here. The comparisons that I showed you for enhancements were all with bulk viscosities. So that's our observation there. And with both molecular dynamics and dissipative particle dynamics simulations, we see that to answer that, looping back now, to answer that question about whether there is this level of enhancement or flow reduction, we are leaning more towards this evidence using these multiple experimental techniques and simulations that we have seen. Another takeaway is that the flow is affected by how the fluid actually interacts with the wall. That means that single phase permeability will not be the same and will need to be adjusted depending on how strong those wall surface interactions are. That means that we will have to make an adjustment to Darcy's law as we, single phase Darcy's law. And then of course, we have to take it from there to the multiphase. So I think this is a fairly significant finding. We do have to quantify this effect more thoroughly, but this is what we are seeing with the multiple pieces of evidence that I presented to you. I do have, anyway, as we move forward, we are going to look at viscosity measurements. We have made these nanochannel devices using this, what we call a viscosity chip in a clean room, that will help us look at viscosities as a function of shear rates, and see if we can validate some of the models that have been predicting certain type of change in these systems. I think I will stop at this stage. If there are, I do have a set of slides on thermodynamics, which I will not use at this time. I think I will try to answer some questions as we go forward.
Yeah, thank you, Professor Dev. So to begin with, I think we have one question in the Q&A panel where Mr. Pramod Nayak is asking, how does the flow rate depend upon the surface charge density of the nanoporous or mesoporous materials?
Yeah, that's an interesting question. We really haven't looked at the charges in this particular system. We are thinking that that is not going to have a significant impact because of the extremely large pressure drops that we impose both in the models as well as in the experiments. But another group, the Wyoming group, is looking at the surface charge issues and differential flows that could be set up because of that. That's definitely a consideration, but for the type of systems that we are looking at, it may not be a big factor.
Okay, so they also have another question, and they're asking if you have tried to work on fluid flow using emerging 2D based membranes.
Yeah, we haven't looked at the membrane flow. There is a the group at Cornell is looking at aluminum oxide membranes that you get, I think, with a certain pore size that are almost 2D. That again will have to be pressure sealed to be able to perform experiment. That's a good idea. I think that's something that can also be used for studying these relationships. We haven't done that though.
Thank you, Professor Dev. We also have a question by Mr. KG Gopinath here, and they're asking if any studies or experiments have been done on methane clathorites.
Methane clathrates, no, we haven't done any experiments. So those are, yeah, more reactive systems, I think, in some ways, looking at either deposition or dissolution. But yeah, methane clathrates specifically in, we have not looked at those systems.
Thank you, Professor Dev. So do we have any further questions from the panelists or the audience? Yeah, Ramesh, please.
Yeah, thanks, Professor Milind. I think it was an interesting talk. My name is Ramesh, and I'm also a part of this group at IIT Madras. So I have a question on this. The way you're quantifying the flow. So you are using the Haagen-Poiseuille's flow equations, right? So, but actually the porous structure is extremely complex and heterogeneous, and there is a network of channels that's going around, right? So is that approximation of using Haagen-Poiseuille's is fine? And also the other question is, like, you also try to use Cauchy-Kallmann equation, right? And it has some sort of an empiricism in terms of tortuosity. But I think, like, with the tools you have this XCT and you have this MD, where you can actually quantify the tortuosity, then probably you can get a better approximation, right, to the flow. So your comments on that will be good.
So that's why I mentioned initially, as I said, we started off thinking that this would be fairly clear to establish. I mean, answer one simple question. Would you actually, if you have a 10 nanometer channel, are you going to have enhanced flow, right? I mean, it's a very simple question you would think to answer, but that means you have to build something that is reasonably long and continuous and has a 10 nanometer diameter, and that unfortunately is you can use the 2D membranes as people are talking about, but you have to make sure that there are no bypasses or any cracks in how you seal the system, because you're looking at pressure drops of I don't know, several megapascals per centimeter. So it's a pretty large pressure drop that this membrane has to withstand. So insofar as MD simulations are concerned, Ramesh, those are on single tubes. So there is no approximation with respect to, so you are just using Haagen-Poiseuille, but there you are using a modified viscosity, which we are not, I mean, it is modified, bulk viscosity modified to pressure. But again, because we are looking at an extremely large pressure drop, we don't know whether that approximation that we are using is appropriate. That's why we are spending quite a bit of time trying to figure out what viscosity ought to be in that system. The packed system with particles is an experimental system that currently we have capability of using, and it has been done at least once so we thought that would be one way of establishing whether we have significant change from the Cozzini-Kármán relationship. And since there is that empiricism, and we can only measure porosities to certain accuracy, that's why I said that if we see changes plus or minus even one order of magnitude, which we are seeing, I just scientifically or from an engineering judgment perspective, I feel that that is not enough to tell us that something different is happening in the pore space. So that's why I said those differences could be for any of those reasons, that we may have a small bypass, the Cozzini-Kármán relationship that we are using may not be the right fit for that particular. So my take on that is that that again, there is not a significant deviation. So all of this basically, I mean, we are trying to get some quantification of what we are seeing, but also some understanding of what should our approach be to handle these nanoporous natural materials. And from what the nature is telling us, and also from what we are seeing from various methods, I feel that it may not be realistic to have those very large enhancements that people have seen in CNTs. So those I don't think are valid for the type of system that we are looking at. Anyway, kind of a long answer, but
it's okay. You give me some answer, so I think it's good. The one more, I just wanted to ask you one more question. So the rheology of the injecting fluid, it will play a role. So that, have you tried to quantify it, and does that has an impact on the enhancement?
Yeah, it has a big effect actually. Yeah, that's true. It is, as you can see, there is shear thinning, there are all kinds of things going on. Yeah. So right now also, even this chip that we're showing is only, as you can see, 20 microns deep. So we are filling this up with either SBA 15 or 16, and then essentially making nanochannels within this pore space to see if the behavior in the microchannel of shear thinning changes as the pore size changes. Those experiments are not completed, but we do understand that that has a big effect. And actually, that's a bigger, I think, consideration than the changes in the physical laws. And it will have, I think, a huge implication in sensors and membrane preparations for desalination, any of those applications.
Thanks, Professor Milind.
Okay.
Yes.
So we have another question here in the Q&A panel. It's from Mr. Milad, and he's interested in knowing the mechanism of your mini viscometer. He wants to know if it was used, if it uses a pressure sensor or a dynamic interpretation of viscosity. And if it does use a pressure sensor, then what is the sensitivity and the pressure range for these chips to work on?
Yeah, off the top of my head, I used to know this because we just, this is from a partnership with a company that we have worked with for quite some time. It's called RioSense. They make these devices. It is a pressure sensor. That is the main, so it's not a dynamic, so there is a pressure sensor. It goes, I think, to something like, yeah, don't quote me on this. I think something like 20 MPa. It's a pretty large pressure value, and sensitivity. I can definitely send it. If you can send me an email, I can send you the specifications of the transducer. But that is the specialty of the chip, that it does have embedded mini pressure transducer to do the measurements. I don't think there are very many out there that can do that at that scale.
Great.
So it's a good tool, I think. Yeah.
Are there any further questions from either the attendees or the panelists?
I think I had a similar question that Milad has asked, for particularly for what about these low shear viscosities? Will they be measured using this particular rheometer on chip? Because at low shear, it will be highly viscous.
Low shear. Yeah, low shear. I think they do have different chips for that. We didn't get that particular version of it, but they do have for polymers particularly extremely viscous fluids. They do have for low shear flow different pressure ranges and different capabilities. But I think it's available as well.
Okay.
So Milad is asking requesting you to tell him the name of the company again, which provided the pressure sensors.
RioSense. It's like rheology, but RHEO, then SENSC. RioSense, all one word. They are in California, I think. It's a small company. Yeah, it was created by actually a PhD from University of Utah. So that's how we work closely with the company.
Okay. So there aren't any further questions. Once again, I would like to thank you very much, Professor Deo, for taking the time to give this informative talk. And as you mentioned, there seems to be a lot of synergy in the topics that your Energy Frontiers Research Center is investigating, and the kind of things that we would like to investigate here. So we really hope that we could collaborate going forward.
Yeah, we also have, of course, our departmental webinar, and we have a seminar series from Energy and Geoscience Institute also. So I might ask you or your colleagues to participate in those. I think that would be a good way to start. And unfortunately, under these COVID times, we cannot move around freely. But I do think, that there are a lot of synergistic opportunities in subsurface science and technology. And there are some unique things that are happening here in Utah. I think that we can all utilize.
Yes, sir.
Sure. Yeah. Thank you so much.
Thank you. And if you are in this area, by the way, I mean, when things start again, the travel, the Milford site that we have is open, I think, to the public, and it's about 4 or 5 hours from Salt Lake. Out of nowhere, it's actually closer to Vegas than to Salt Lake. But there, I think that second well will be drilled this fall, and
Okay.
that itself, by the way, you could have a seminar just on Forge by one of our principal scientists that would tell you what's happening. All the data there is public as well, so it will be a very it's a project that I think has a lot of potential.
Okay. Yeah. Yeah, that'll be certainly great, especially getting access to the data to validate some of these models at a field scale. I think that would be really fantastic. Yeah.
Excellent.
So we have a request here from the audience that they want to, if you have the time, to finish the thermodynamic part of your presentation also.
Okay.
Yeah.
Absolutely. Okay, let's go through that then. Again, the question that we asked ourselves was rather simple. We said, I showed you that Bakken plot where the gas oil ratios appear to take much longer to go into what we call free gas flow compared to conventionals. So in conventional, usually if the bubble point pressure is not very much below the initial reservoir pressure, then within a few weeks or within maybe a couple of months, you can expect free gas flow to start. And then the gas oil ratios increase. And as you know, gas, of course, has 1,000 times less viscosity than oil. And as a result, it starts dominating flow. And that's, by the way, happening quite a bit in the shale place, where you have these wells gassing out, as they call them. So that's one factor that lowers the liquid recovery in some of these systems. So anyway, so idea was, okay, so is the bubble point suppressed in the first in these reservoirs? And there is some evidence here. You can see this direct visual evidence that came out actually after we started the project from Sinton's group in Toronto, where they showed these capillary measurements and indicated that the bubble points actually were suppressed for this mixture. This is a gas mixture, more or less, which has, I think, some butane in it, but mostly methane and propane. And the bubble points, in fact, were so low that they were suppressed below the dew point of the bulk mixture, right? So that's what you see in this picture. Is the dew point curve is here, bubble point curve is here, and then you can see some of the bubble points, some of the last bits of liquids from these nano channels came out below the dew point of the bulk mixture. We have used DSC in our own work and did some experiments with silica. Our paper was published back in 2017, but these were indirect measurements. These were not direct measurements like this. So these had more factors than just the nano porosity that this group looked at. But anyway, so the evidence was pointing out that you have suppressed bubble points. So if so you can see there is a group in Wyoming that also found that the bubble point is suppressed. So we went ahead and did some experiments of freezing or melting transition of water in the materials that we ourselves made. So this one is, I think, SBA15 with the cylindrical channels, SBA16 with this bimodal structure, and then FDU5, which also has a pore crossing by continuous pore, which is all made by us in our center. And for the first time, we were able to see these two transitions for SBA16 and for FDU5, and one transition for SBA15. So this paper was also published in Scientific Reports, I think, in 2019 or so. And then we were able to take that data, the suppression data, and put it on a Gibbs-Thomson relationship to show that it actually does fit the freezing point suppression in under nano confinement that based on the pore size that the Gibbs-Thomson relationship predicts. So we were able to we were quite happy to see that we are able to do this. So this is one part of the story. So this is almost complete, I guess, in some sense, and the paper is in Scientific Reports. The second part of the story is somewhat incomplete. So we're also looking at boiling point transition using DSC. So we were able to confirm some of the things that Sinton's group saw, which is that we were able to see the so-called confinement peak well above the bulk peak in a high pressure, high temperature differential scanning calorimeter. We have two of them, one that goes to low temperatures and high pressure, one that goes to high temperature and high pressure. Anyway, so these, and then we were able to repeat this for an entire set of pressures. Again, we were able to generate a vapor pressure curve for heptane and for toluene. And in all cases, we are able to see that the curve shifts below the bulk curve. Okay, so, but still we are not able to answer this question. Is this because the bulk actually completely envelopes the confined fluid? That's the only way we can prepare this mixture, right? When you fill these pores, you're going to fill the nanopores, but also you're going to fill what can be considered the bulk that's surrounding the nanopores. So does all the bulk have to go before the nano fluid evaporates? At least that's what the DSC data, this DSC data is telling us. We have some new DSC data that I don't have on this set of slides, where we created a technique to fill only the nanopores and leave the bulk pores alone. And that actually shows suppressed, earlier transition compared to the bulk, and we're still trying to get our arms around what is going on there. So anyway, so that is this story. And then we were able to use Gibbs ensemble Monte Carlo simulations. These were done again at one of my former PhDs in Manas Pathak initiated these, but then these were taken over by Idaho National Lab. We have to use some type of interval wall interaction parameter lambda that defines the interaction between the wall and the fluid, and that then determines whether the transition happens, the boiling transition in this case happens before or after the bulk transition. So here are the experimental observations that we see for confined heptane and confined in SBA 15 and 16. And the GEMC simulations more or less match that, but not quite. So there are some deviations that we see. So again, in this particular study where the bulk actually surrounds the confined fluid, we do see a confined transition that occurs later than the bulk melting point, which corresponds, by the way, to a suppressed bubble point. So if a higher melting point means suppressed bubble point, which somewhat confirms the hypothesis that maybe the transition of to vapor phase in shales is delayed because of the pore size. We are still looking more into this. There is, with the Monte Carlo simulations though, if you change the lambda factor, which if you make it weaker, for example, you can have, it basically shows that you can modulate when the transition actually occurs, and sometimes it can even happen before or after. So it is, it depends on whether, for example, you're dealing with graphite or silica in this case. And this particular observation, I guess, using GEMC, we have not confirmed it experimentally, but using molecular dynamic simulations, it suggests that if you have a hydrophobic surface, you're going to behave a certain way. If you're going to have a hydrophilic surface, it's going to behave another way. But that we have not yet confirmed experimentally. But the bottom line here is that the behavior, the thermodynamic behavior of fluids under confinement is affected. That the transitions are going to be at sometimes significantly different conditions than in the bulk. And there are good theories and models to explain that. So again, there's a takeaway from here. Phase transition occur in the bulk fluids first. Is this due to the bulk fluid masking the confined fluid? This might be yes to this answer. And then modeling suggests fluid wall interaction may influence when the confined fluid transitions occur, and the experiments currently are underway to test that hypothesis. So that's my thermodynamic piece. But it's quite exciting, I think, to look at these phenomena and at various scales and using various experimental tools available to us. Thank you.
Yeah, thank you once again, Prof. Dev. So are there any other questions on the second half of Professor Dev's talk?
We are looking at binary systems too, and those are not that easy to investigate. You really have to recreate that system. It's not easier to recreate it in the bulk itself, but then you have to somehow make sure that what you fill in the nanopores is the same as what you started with. We did report binary experiments in that 2017 paper, but in a DSC, it's another ball game altogether. So.
So if there are no further questions, well, thank you so much, Prof. Dev. We really enjoyed listening to you speak, as well as interacting with you through the Q&A sessions. Thanks for patiently answering all the questions. And as I mentioned earlier, we hope that we will take this interaction forward and continue collaborations with your center.
Yeah, thank you. Yeah, I know that it's late hour there. Today is what, Ganesh Chaturthi also, right?
Yes. Yes.
Thank you for joining at this late an hour and continuing this webinar.
Thank you. It's our pleasure. Yeah.
Yeah, thank you, Professor Deo. Again. Thanks.
Okay, thanks.
Bye now.
Bye.